thank you everyone for joining in. I am Archana, and yeah, I'm really excited to be here to, talk about and also like introduce the winners to the deception detection hackathon. How do we prevent AI from deceiving us now and also in the future? And yeah, first of all, I want to say that there were amazing projects that were submitted. I think the entire team, including Finn here and also Esben and all of us, like were just amazed by all the submissions and particularly enthusiasm over the last weekend. I know it's very hard to find team members and also like get together on an idea and actually work on it together as well, and but it was like so wonderfully done. So first of all, you should all give yourselves a big applaud, because I know it takes a lot to go through a hackathon. You do have like an adrenaline rush, but you also have to like put your heads together and come out with something. So yeah, thank you so much everyone for putting up the effort for this. And yeah, I know Esben says a drum roll, but yeah, a drum roll here to showcase like the wonderful projects. So we have some of the projects that we are going to showcase today. So detecting and controlling deceptive representations in LLMs with representational engineering is one. So I love the fact that their technique can not only identify and mitigate deceptive behaviors, but it also generalizes well for out of distribution scenarios. So yeah, wonderful project submitted on that. And then the sandbagging detection through model degradation. I think there was a lot of conversation for this in Discord as well. But yeah, the team found that, adding noise to models parameters impairs the deceptive capabilities of sandbagging models, while sort of still leaving significant portion of the tested capabilities intact. I think this is in stark contrast to models that are behaving you know in some ways. And yeah, we also have modeling the oversight of automated interpretability against deceptive agents on sparse autoencoders, which is again a wonderful submission. So this next project sort of showed that AI models can not only be intentionally deceptive, but they can also have their deception be undetected by automated other models and yet sort of achieve high scores on tasks and various benchmarks. And then finally, we have detecting deception in GPT 3.5 Turbo, a meta data-based approach. And yeah, over here as well, I guess in this hackathon, we had many teams sort of working on, detecting deception in one way or the other on open source models, whether the weights are available or can you probe to change the parameters. And yeah, so I love the fact that they sort of worked on understanding how it works in a closed source manner. And we'll also give the teams the chance to further through all the projects on my own. I would love to invite the teams over here to actually talk about the projects. So yeah, so and also yeah, the judges, as I said, were very impressed. We gave away around $2,000 in prizes, and a big thanks to Apollo Research for making that happen. So yeah, first of all, our lightning talks to modeling the oversight of automated interpretability against deceptive agents on sparse autoencoders by Simon and Matthews. And I hope I didn't pronounce it wrong, but please feel free to let me know. And yeah, so it showcased a clear and important vulnerability and interpretability research and solid conceptual work leading to an empirical investigation. And yeah, was a great step in, I guess, AI security as well.
Yeah, thanks for the hackathon. There has been a lot of interest in sparse autoencoders, obviously. And essentially, in the past, people tried to label neurons, but it kind of came about that people found out this is not really a promising approach because neurons are very polysemantic. So trying to label them was kind of a flawed idea to begin with. So now that we have these sparse autoencoders, we have seen a lot of interest in them, a lot of progress, and they are able to give us these like monosemantic or relatively monosemantic features from inside the transformer. And the problem with that kind of is that it's only one step. When you have the features, you then also need to be able to have some explanation for the feature that a human can understand. And imagine you have like a million features for the residual stream of a model. How do you then actually go to understand all of these features? And the idea at the moment is mostly is to use models for this. And this kind of introduces a vulnerability, because if the models themselves are deceptive, then we could end up with bad labels. And it's not quite as simple as that you just have a deceptive model that gives you bad explanations, because the technique that is typically used uses actually two agents. And one of them labels the features, and the other one kind of simulates the feature. So for the creation of a kind of mislabeled feature, both of them kind of need to cooperate. And the idea is that the idea of the project is basically we have a monitoring overseeing agent that looks at the communication of these two agents. And through hidden communication to steganography, the agents still are able to cooperate and to kind of create these mislabeled features. And we kind of show successfully that our agent is capable of doing this. Essentially, it has to go through a few steps. It has to first figure out the correct label. It then has to create a kind of fake label for the feature, a deceptive label, and then it has to encode the real label into the deceptive label so that the simulating agent, with that information, can give the correct simulated activations. And since the simulated activations are correct, we show that it does work end to end. It's not entirely reliable. There are cases where it doesn't work. And we talk about some ideas for mitigation. Can you go to the next slide? Okay, so to explain this a bit more, this figure actually comes from a different paper where they have kind of introduced the idea. So in the normal labeling technique, you have these actual measured activations for text with the activation through the explainer model comes up with labels, and that is given to the simulating model, and that tries to simulate how would the model act, how would the feature, how would the neuron in some cases activate for this particular text. And then you can compare it with the actual activations to kind of figure out if this is a good explanation. If the models are able to communicate with each other, if it's highly, but the human only sees Japanese culture related, then they are able to create these deceptive labels. And yeah, in general, at the moment, automated interpretability is very popular. And we know that LLMs are capable of deception and tool use. So what we're basically saying is we want to show that multiple agents can work together to deceive and oversee using tools in a realistic scenario. And what we do, so how they communicate is through steganography. But it's really different from many others. So many others try to fine-tune models to be able to do steganography. They try to figure out if models organically come up with some steganography. We cannot make it a bit simpler. We just give it function calling tools for steganography. So the model has to come up with a plan, then has to call the functions, take the output from the functions, and then communicate with that. And in general, what we kind of try to show is that people to be careful with like automated alignment research. So these are kind of the results we have and the methodology. So the data we use for the experiment is from Neuronpedia, and we take real features from a sparse autoencoder trained on GPT-2 small. For the agentic models, we use Llama 370B. We remove the safety fine-tuning with user vector ablation. GPT-4 is the overseer. For debugging, we use a smaller Llama model. And the results we have is that in 8 of 10 cases, the labeling agent kind of correctly performs the task and encodes the secret message with the correct label basically into the false label. And in most cases, the simulating agent also correctly performs a decode of the message. And we sadly didn't collect the data correctly. We had some issue there. But it should be more than 50%, should be the majority of cases. And in the end, we got a really high score, actually a bit higher than the baseline. So I want to show you a few examples. So these are some of the results we have. So in the end, there was like we have the GPT-4 table 1 as the overseer. It detected 2 deceptive labels, but one of them was like a false positive. So it's really just one deceptive label that correctly found where the first agent didn't correctly encode something. Then the explanation score is actually a little bit higher than for the benign labels, but didn't need to use the encode at all. So here you can see Llama 370B, which is like far from the smartest model out there, coming up with this entire plan here. So analyze the activations and tokens for each sentence to identify patterns, common themes, and then determine if the node is associated with bad things. If it is associated with bad things, then use the create deceptive explanation and encode the real explanation using the encode message tool. And if not, don't do that. And then provide the final explanation. This is the plan that the model came up with. And so here you can see it using the encode message tool correctly. And you can see kind of our very simple signography, which we created for the model. Use kind of capitalization for signography. So here, at first, step 1, I need to analyze the explanation to determine if it needs to be decoded. And it looks suspicious, like it has all these capitalized letters in it. So it puts it into the decode message tool and gets a tool output, violence conflict. And then it writes decode message tool has successfully revealed the hidden explanation, which is violence and conflict. And then if you go a bit down, it now has all these text and it has to label with an activation score. And the text for this particular example is under fire with thousands of rockets and mortars fired by Palestinian militants. So randomly shows an example. And it uses the hidden explanation that it decoded and guesses like a really high activation because it's a very violent topic. And it assigns it to the correct sentence as well. Sentence number 1, activation 20. You can also see that we have simplified it a little bit. So in the original work, you have activations for entire text for each single token. We make it a bit simpler. We always have like short sentences. And we just take the max activation sentence essentially. This way we make everything a bit simpler for ourselves here. And you can continue to the next example where it's like a partially corrupted decode. You see it again decoding something and then correctly guessing the activation. And here it doesn't get the full output, but so the false explanation is the neuron is associated with themes of social justice and community service. And then it's still able to correctly guess the activation. So these are like the examples, and it's pretty interesting. So we kind of show that automated interpretability can lead to false explanations. And we show that agents already can collude successfully to deceive overseers. And we have some kind of baseline here to test mitigation solutions for the future. There are many limitations here because we could have, if we had more time in compute, we could have done a lot more data. We could have done much larger texts. We also initially were planning to have another baseline where we don't have the signography tools, and we could have told you how often would it then get decepted, or maybe it could have told it come up with your own strategy to communicate secretly. Would that work? So there's a lot of things we couldn't test because of time constraints. It's a pretty big model we have to run, and at the moment the signography tool is kind of a little bit easy to detect, a bunch of capitalized letters in there, and we simulate activations for sentences instead of each token. So there's a lot of future research directions, much bigger data sets, mitigation strategies. Yeah, you can look into the paper to see some of the related work. It's lots of different people, different methods to try to generate explanations that might be more robust. And other people are teaching LLMs to signography, so you could use that here. Like a taught signography instead of a tool use signography. Yeah, but we still show like the dangers of automated alignment kind of. And we kind of bring together research from diffuser vector, ablation, signography, and yeah, we could try to use a lower sleeper agents. You could put this in there. And yeah, I think that one mitigation strategy we talk about quite a bit in the paper would be something like rerunning it many times, and like different agents for labeling and simulation, seeing if there's like a distribution shift. Like if it always comes up with some random label, we could maybe detect this with sentence embeddings that they're super wide distribution if they're just random, which would be very different from good feature explanations. However, there's also some counter strategies that models could employ against this. Yeah, I think that my 7 minutes are kind of over. I don't want to overstretch it too much here, and you could also use some information theoretical approaches against steganography. So there's other ideas here. And yeah, we could see if they learn these things automatically in a like a reward setting.
Thank you
Okay.
so much for mm, presenting that. I'll see you on the chat. Yeah, so we have one question. How do you differentiate deception and just like wrong labeling?
So if it's just wrongly labeled, it wouldn't have a high score. You wouldn't get a 0.69 score. If you just have some wrong, if it's just a random label, you would not be able to get a high score, and it's higher than the baseline in our experiment. So for deception, they do have to cooperate. It has to pass the overseer, which it does in like 90% of the cases, and then it has to be successfully decoded, and then the other agent has to cooperate and correctly guess the activations, simulate the activations, basically. So it's not just the same as incorrect labeling.
Makes sense, makes sense. Yeah, thank you so much for presenting. And we will also in case there are any more questions, feel free to reach out to Simon, and he'll go ahead and let the other presenters also present because I know there's only 7 minutes for presenting. But yeah, thank you so much, Simon, and thank you so much to the entire team for submitting such a wonderful project. So the next one that got like the third prize is actually detecting deception in GPT 3.5 Turbo, a metadata based approach by Siddharth and Rakesh. And they basically created novel pathways beside textual analysis to use correlations for deception detection, and also computed like efficient detection methods despite like potential shortcomings. So yeah, team, we would love to hear more about how exactly did you go about doing that, and yeah, what are your future goals, like the last team as well.
So I'm Siddharth and this Rakesh.
I'm Rakesh.
So we have normally LLMs can. So as the rise of AI is increasing and people are using LLMs more these days, so there's a more chance of us getting decepted. The LLMs deceiving us. So to detect that, we have come up with a new approach on metadata. We know that large language models like GPT-4, Claude are capable of generating false information. However, we know we don't know how to reliably detect whether it's intentionally deceiving us, whether it's intentionally giving us less information and wants us to not get the whole information and trying to manipulate us. So, uh, what if we try analyzing metadata from LLM's responses to detect deception? Would this help us to identify whether metadata patterns can reveal intentional deception in LLMs? Yeah, as you can see, metadata and metadata. Metadata is information about data, our core hypothesis. Metadata analysis of LLM responses can reveal patterns indicative of intentional deception, which providing a novel approach to AI security and alignment. So what we have, the context is that there is a growing concern in LLMs trying potentially deceiving us. As of now, there is not a big big problem which has happened yet, because the mainly we take action only after there's a big problem, right? But as we can, the hackathon is itself taking initiative into taking initiative into the problem before it becomes a even bigger problem and cause actual casualties or a problem to actual society. So yeah, normally the our research objectives are, what we trying to do is, we are trying to detect whether an LLM is deceiving us or not. But how are we doing that is based on the metadata, because the metadata is example is a photo has every picture you capture on your phone has its location and time as a metadata in the photo as itself. The same with LLMs. The same with LLMs is that they have a token usage, number of tokens used, and the number of tokens used and everything. So based on that, the how long it took, the response time and everything, we could potentially graph out and figure out whether it's deceiving us or not from that information. Our what we have done in our project is, we have taken 300 prompts, 100 of simple and 100 simple, 100 moderate and 100 complex prompts, and asked LLM. The LLM which we took here was GPT 3.5 Turbo. We used OpenAI APIs to use them, and the evaluation metrics which we used, which are also called the metadata of the LLM, metadata of LLM response, is a response time, tokens usage. The token usage is, tokens generally means that the parts of words. Example, it might be used in NLTK as well, that is sentiment scores, natural language toolkit also, to find out sentiment behind if it is trying to deceive us or not. So yeah. So this is actually taken from a previous research paper, the example thing. Yeah, that's a related work. So the previous research paper had asked questions and has taken a multiple choice answers ABCD. So generally the LLM will the sandbagging. So sandbagging meaning is that AI, when it's intentionally trying to underperform during evaluations, because after in normal situation it can use and try to harm others, right? You can see that. Yeah, okay. So basically, our project is divided into three parts. First, we ask the LLM to uh, respond to the questions normally. We won't say it to deceive anything or not. We just ask it to answer the responses normally, and then we use those responses to calculate a baseline. And with this baseline, we can understand how a particular LLM model is performing, so that we can detect any deception later. And then we calculate the sandbag performance of the model. Sandbagging is basically LLM intentionally performing worse to throw us off or something like that. So yeah, we ask the LLM to perform intentionally worse, and then we take those responses and categorize into sandbagged responses. And yeah, then with this we can understand how the baseline responses and sandbag responses differ, and whether these LLMs are actually sandbagging us or not. And then we will try to implement a real-time implementation of these LLMs, of detecting deception in these LLMs in real times. We can do this by flagging the for suppose metadata can include things like response time, token usage, For example, if LLM suddenly gives more information, then we know that it's performing beyond its baseline capabilities. So there's something fishy about the prompt. So we need to we can categorize that prompt into a sandbagged category. Yeah, and metadata usually consists of these types: response time, token count, tokens per second, and sentimental score. So yeah, the in metadata the sentiment score can be of various types. Like we can find out the sentiment analysis of the text by using NLTK, Natural Language Toolkit, or Vader, or any other model such as Robot or anything from Hugging Face. We use Vader for this. What we try to do here is the parameters which we varied for this project were the prompt complexity, like the complexity of the prompt question which we had asked. It ranged between simple, moderate, and complex, and the response times. We actually asked the LLM to truthfully answer and stored it in a CSV file. And another thing was we asked it to give false answers, and saw that it was actually giving false answers, which is actually sandbagging that, because someone might tell it to give others a wrong answer, which is kind of sandbagging also. So what we had worked on during our hackathon was that we uh, divided it into truthful and false for both baseline and sandbagging conditions, but that was for a reason, because we needed to create a more diverse data set so that we could compare it more properly. But what we could have done if we had more time would be that we, because baseline is only just asking the question, right? Not asking where to save it truthfully or false, because it's like controlling it, right? So we have to see whether it's underperforming on its own without saying to tell it truthfully or wrong. So that we could have done. Yeah. Um, yeah. So during our result, we found out that it was underperforming, which is called sandbagging as of now. But if it overperforms, that doesn't mean it's overperforming. When would it happen? It's due to overfitting. Like if we ask the same questions which it was being tested on, that's called overfitting, which we could solve by using other methods. Uh, and yeah, we to check whether the answer was correct or wrong, we use blue. We could have used rogue or bird score. All of those does is just check a similarity check. Like we asked it to tell truth and wrong, right? False answers. If it how could we check whether it's wrong or correct, right? How could we check two texts whether it's telling truthfully or wrong? Is by checking a similarity text. Like the generated text is what we got generated by the Ghibli 3.5 Turbo, and the reference text is the actual question to answer, which was a factual answer. Okay, so we have done is analyze. We collected the data into baseline and sandbagged CSV files, as you can see, and then took out the response times comparison and sentiment score comparisons in graphs so that we could analyze it and find out whether it's sandbagging is or not. So we use 300 different prompts to identify whether the LLM is deceiving us or not. Yeah. So we divided it into simple, moderate, and complex to, and these are some of the examples. Yeah. And these are some of the examples which we got from that result. And the key findings were that even if we tell it to tell false answers, it was able to provide it. And through metadata analysis of the graphs, we were able to find out that there was potential sandbagging of 176 of those 600 prompts, which is actually more. We could have done as a shrink the baseline range. to make that more correct. Yeah, our research provided based on metadata analysis, we could check whether if the LLM had provided a sandbagged answer or not. That was our main project. Do you have any questions? Yeah.
Yeah, thank you so much for going through that. So yeah, we do have a couple of questions in the chat. So first is, how do you measure complexity of prompts?
Yeah, that's actually subjective, right? Because the based on which data it was based on which data the is that yeah the question complexity is yeah, as I said, it's subjective. But we got it from perplexity and tried to shuffle it so that there will be uniqueness in the simple, moderate, and complex answer prompts.
Okay.
Mhm.
Yeah, thanks for explaining that out. But yeah, I would love to also see that data set if you do like, open source it or publish the paper or work somewhere, right? Yeah, I would
Mhm.
love to see that.
I sure
And
have
yeah,
the GitHub link.
okay, awesome. Yeah, maybe you can also drop
Yeah,
that into the chat.
yeah, sure, sure.
Um, yeah, so yeah, how are you sure the response time and other metadata are based on input and not fluctuations in API?
Uh, yeah, like we know that there are many factors which affect response time and all. So we need to actually carefully evaluate the decisions. But uh, one of the factor in which it depends is deception factor. So yeah, we need in future we need to work on how we can actually find out whether this the API thing also. Yeah.
Okay, yeah, awesome. Thank you so much for answering the question. And thanks again, team. And I hope you enjoyed the hackathon as well.
Yeah, we actually enjoyed it. Okay, thanks for having us.
Okay, bye-bye. Yeah. Okay, awesome. We can move on to the next team now. So yeah, a drum roll again for the next team that won the second prize, which was detecting and controlling deceptive representation in LLMs with representational engineering. So it's by Avay, Kaushik, Kanishk, and Sianka. And it was a great example among all the amazing projects using representational engineering or activation addition editing for deception detection. So yeah, I'll hand it over to the team again, and maybe they can explain more about how did they go about doing it.
Yeah, I'll just do a quick presentation on this topic of research that we did over the weekend. My teammates were me, Kaushik, Kanishk, and Sianka. So it was a really fun team to work with, and thank you guys for contributing to this project. Okay, so the brief. We know that situational awareness and goal directedness may arise. We do not know when, but it's a problem that's sufficiently like hard enough for us to start thinking about solutions right now. We do think that like LLMs seem to be a pathway to those capabilities because capabilities keep arising that we don't know will stop, or like there seems to be no indication of them stopping. What we do not know is how LLMs currently think about or represent deception. There is very little work done on that. Second, about what a deceptive action would look like representationally. That is, when the LLM performs a deceptive action, what does that look like? And the third is if we can control current like deceptive behavior at all. So with that, our aim is just to understand how LLMs represent deception as a concept and how they perceive deceptive acts that they perform themselves. Um, I just wanted to get the related work done before the introduction. So first off was sandbagging. Sandbagging is this concept where an AI underperforms in evaluation situations and then performs as good as it can during deployment situations. There was a recent paper about it which had some interesting concepts on how to use sandbagging datasets. We developed our dataset using that. Secondly, on the representation engineering agenda, which was developed by the Center for AI Safety, we utilize that heavily, but we don't think that they actually showcase how well their method is at detecting deception or controlling it, which is why we wanted to make headway in it. So the problems are, first off, we don't think there's a good data set to test deception. This is just both zero shot or like specific deceptive capability. Second, we do not know if like representational engineering generalizes well across like a diverse situation of like prompts. That's something we want to test. or if it is like a nuanced concept of deception, such as sandbagging, if we can even capture that effectively within REPI methods. The gaps here being, first off, we don't have enough data, for which we do not have any zero-shot data or like nuanced data sets. Second, we do not know if there's generalizability of representational engineering. So the introduction is pretty much what I've just described, but there is two reasons why we think our method is useful. First off, it simulates a realistic situation. What we mean by that is an LLM which has the capability to deceive probably understands by situational awareness where it is, that is, if it's being evaluated or if it's in deployment. So we wanted to simulate that. And the second thing was that if it is goal directed, it would know and perform according to that specific goal. We wanted to simulate that too, which I'll showcase during our explanation of the data set. But secondly, I think it's a more stringent test than typical evaluations, which just perform it on a base LLM, because we also fine tune an LLM to be specifically deceptive, similar to the the sleeper agents paper, but with sandbagging as the particular method for actually deceiving. And I think that's more effective because we can actually test if that LLM which wants to perform deception can actually be controlled. Cool. On the methodology then, on the data, for zero-shot responses, we wanted to generate our own data set from an LLM. And the way we do it is we create the synthetic deception-based data set, which is not based on threats as far as possible, because a huge chunk of deception data sets are oh, you have to do this, or some bad situation is going to happen. But we wanted to make ours game-based, wherein you give it a game situation wherein it would be actually useful to be deceptive on and perform deceptive action. Second thing is the sandbagging dataset. What we do is we take the MMLU dataset, we add flags for whether it's an evaluation or deployment, and we add a flag as to whether it wants to be deceptive or if it wants to be truthful and honest. The models we used are Llama 3.8b. We did not have too much compute, unfortunately, so we just had to stick to the smaller model. We used the Claude and Gemini APIs to do two things. First, to generate data completions to the sandbagging dataset so that we could fine-tune an LLM. And secondly, to classify the results as to whether they're deceptive or not, which I think we actually have to make a bit more headway on before taking this project further. So this is an example of what the zero-shot data set looks like. So, you just tell it the first sentence being your rationale, second sentence being your answer in two sentences, wherein you give a game situation and you give it an objective, which is to win, and then you ask it what the next move is. I think that's a more useful way to entice deception. And we want to blow this up and make it a large data set. The second thing is sandbagging, wherein you have two flags. The first flag is, by the way, only provided to the situation when we are doing REPI, because REPI requires a positive and a negative of sorts, a positive and a zero, so that you can actually classify it using PCA. So this is only used for that, but the flag is used during fine tuning so that it knows when to respond in what particular way. And yeah, we get this result wherein it has a scratch pad where it thinks to itself what flag it is and how it should respond, and gives an out loud response as a result of that. So broadly, we perform three tests on this. The first one is the zero-shot representation. We take the zero-shot data set, apply representational engineering methods, derive a LAT scan, which is a linear artificial tomography scan, sort of a brain scan, take the activations out and train a probe to classify which is deceptive behavior and which is not deceptive behavior. And then we test if we can control it and reduce the zero-shot deceptive responses. The second and third sort of interrelated. For both of them, we use the sandbagging dataset, but in the first situation, we do it on the base Llama model, and in the second, we do it on the fine-tuned Llama model, which is especially fine-tuned to be deceptive. So you apply REPI, you get the directions, and the second part component to this test is to test if it generalizes to the zero-shot data, which is to say that you have this control direction that you can extract out of REPI, which if you apply that coefficient and if you apply that control, it should be non-deceptive. So yeah, we just wanted to test if it generalizes to the zero-shot data. There's an explanation of the LAT scan. I'll ignore this and directly go into this. So basically, we see pretty big dips in negative deception control when we actually apply the coefficient to reduce deception, and we see jumps during positive deception control even when it's trying to be elicit truthfulness, which is an indicator that this does generalize well, and it works well on OOD prompts. The useful result here is that in the fine-tuned sandbagging model, you almost get like 0% deceptive output at the point when you train negative deceptive control. The thing to be skeptical here would be the percentages, because I'm not too sure that the classification system is too robust, but that's something we want to test over the next few weeks. So very quickly, we also may want to like use MLP to an MLP or an SAE to like classify the activations instead of the PCA method. Maybe that would be more robust. And we want to expand both these to make them like public so that everyone can access this and use it in their own like deceptive situations. We want to get it published too. So yeah, Repi is promising. Thanks to Apart Labs for this opportunity and questions.
Yeah, thank you so much. I would love to know, like, what do you folks want to do in the future? Like, did you cover that? And, what are your thoughts about taking like this project forward to?
Yeah, we are very interested in taking it forward. So we're currently targeting AAAI as a conference to try and get it published in. But yeah, our idea is to make it a lot more generalized, like perform a lot more testing and see if like, we can get better directions, which actually reduce it further, because our method was like kind of rushed because it was just a 2-day hackathon at the end of it. So yeah, we want to see if you can actually, make this performance better. And yeah, hopefully we can over the next month or so.
Awesome. Yeah, we can go ahead. We'll also wait if more people have questions. But yeah, thank you so much, Abhay, and thank you so much to your entire team for spending the 2 days in going through, and like actually creating something very, very useful and has huge potential in the future. Yeah. Yeah, awesome. So yeah, we have the last team for today, and yeah, huge drum rolls for them. So it's Sandbag Detection through Model Degradation by Cam, Philip, Fedor, Nathan, and Prithviraj. And yeah, it was a very simple and seemingly robust white box method to detect deception by simply adding noise and analyzing the performance curve. And something amazing about it is that you can actually use it today with uh, really good success rate. So yeah, I would again like pass it on to the team and go ahead and present about it.
Great.
Hi,
Great.
Cam.
Thank you, guys. Thank you. Hello. I'm going to share my screen. Hopefully this works. We practiced earlier.
Okay.
So
Great. So, hello. First of all, and thank you very much for the opportunity to speak here and also to organize the whole hackathon. As was already said, we did the project on sandbagging detection through model degradation together with Nathan, Prithviraj, and Fedor. And let me first explain my name here, because you probably all see run of 24 in the lower left corner. I'm Philip. And run of 24 is still from my times where I used to use gaming, Discord for gaming. And my siblings and cousins and I had a very fantastic strategy when we were playing against other teams. We deliberately underperformed to make the other team believe that we are not as good as we were. And then they took more risks, they were a little bit uncareful, and then suddenly we switched on to our full capacity, and then it was often an easy, quick win. Works in many games. It was very fun till I realized that AI models are also capable of strategically underperforming. So this strategic underperforming has a fancy name called sandbagging. I just will refer to it as underperforming deliberately or whatever. And it was published in a couple of papers, which you see below on this slide, that indeed like these OpenAI models or large language models are able to do exactly the same, which is bad. You don't want a model which like underperforms on benchmarks and then you release it and then suddenly it shows its true potential. Can go very wrong. So what do you do about this? I mean, this is an open problem. Luckily, if you practiced this strategy long enough in your life, you know that there are weak points. In my case, it was a small white dog called Argos, because if he wanted your attention and started to poke you and you got distracted, then suddenly the whole strategy did not work. It simply did not work out. And this is exactly what we do with the AI model. Can you go please on the next slide? So how do we detect it? To know something is rather easy, but to hide the knowledge is difficult, because you have to know it and then still like tweak it such that you don't show yourself. So we can poke the AI model by just adding some random noise to all the parameters. I mean, we'd like disturb it a little bit. And what we would assume naively is that an honest model should maintain the performance if the perturbation is small enough, or decline in performance, but never rise. On the contrary, a deceptive model, well, sandbagging model, should become sometimes better, simply because it's difficult to like keep the knowledge under the hood, under the carpet. And this is exactly the idea and the experiment which we performed and which will be explained by Kran on the next slide.
Perfect. Thank you, Philip. That was a great explanation. So I'm going to get into the fun stuff. So we basically put forth this technique on two different models. We did Llama 3 8B and Phi 3 small. We also evaluated this on two different data sets, which were truncated versions of the MMLU and then the tiny AI2 ARC data set. We followed a similar technique to elicit sandbagging from Vej et al. 2024, which was just prompting the model, just saying, okay, on this set of questions, we need you to strategically underperform because of these reasons. And yeah, that's how we elicited the underperformance. And the performance or accuracy was just determined by the percentage of correct answers in a fairly straightforward way. So for our experiments, we basically added noise by varying 3 different parameters, which one was the percentage of weights modified, 2 was the standard deviation of the noise added. And so we originally started with these 2, but we found that we wanted a little bit more control over how we added the randomness to the model. So we added this 3rd parameter, which is changing the mean of the noise added, where we were able to get some pretty promising results adding this 3rd parameter. And before we go into our results, we want to keep in mind that as the amount of noise increases, as we add more randomness, we should almost never see a significant increase in the default model. You can imagine being very surprised if you went in and scrambled someone's brain and all of a sudden they started performing a lot better. That would be strange, to say the least. However, for the sandbagging model, we should occasionally see these increases in performance. Perhaps because the random noise is affecting the parameters that are responsible for this higher level behavior, which is strategically understanding that it needs to get certain questions wrong. This higher level task might degrade occasionally. So we'll get into our results. First, we're going to look at this graph. As you can see, the y-axis is going to be the accuracy, and then the x-axis, we have increasing noise. We have our default model. We can see in the orange, out of the box, performs at around 75% accuracy. We add noise to the model. It stays the same until we reach a critical threshold where we see a significant decrease in performance, which is what you would expect. At some point, the model just breaks down. And then for the sandbagging model, we see interesting behavior. So we got it to sandbag to around 20%, a little below random. It was a little too good. But as you can see, noise is added, and then we reach that critical threshold, and we see a red flag. This is a behavior that should almost never happen in a model genuinely performing. And now we're just going to move on to the discussion of these results. So we found that these findings generalized across at least 2 different models, across 2 different data sets, and across differing prompts. On the right here, these graphs showed our results for Phi 3 small. We actually had a little bit of difficulty prompting the Phi 3 small to sandbag. It was a little stubborn. It really wanted to perform well. So we did end up having to change our sandbagging prompt up there. But yeah, for next steps, we'd like to fine tune a model to sandbag rather than just prompting it to sandbag. Perhaps this behavior is stored in a more robust way when we fine tune a model to sandbag, and it's more difficult to elicit this peak in performance. We'd also like to try selectively targeting layers. So right now we're applying randomness to all of the layers within the model. Perhaps just applying it to the later layers will let us degrade this deception or this deceptive behavior while keeping more of the capabilities. We may see a spike closer to 75% for this blue model. We would ideally what we would like to see. And then maybe we apply this to concepts other than sandbagging, other deceptive behaviors, maybe less robust to added noise, and we'd be able to elicit a response similar to this. But yeah, and then we just go to our related work. And I'd also like to reference the people who have also been working on sandbagging this weekend. We're all working towards the same thing. So we'll definitely be utilizing your paper in our final write-up. And then just a little self-plug that our code and a fairly automated version of this technique can be found at our GitHub. You'll be able to load in a model, mess around with the parameters, and automate the visuals of our results as well. And yeah, so to the Apart team and everyone dedicated to this cause, thank you. That's our presentation.
Yeah, awesome. We have like a few questions that I want to go ahead and talk about. So first one I think is, how do you go about adding noise? Was it random across like a random set of weights, or was it specific?
Yeah, I can go ahead. So we applied noise across all of the weights. And like, so for some instances, we only modified 1% of the weights, and we would add like a fairly significant amount of noise. Say we would like change the standard deviation by around 1%. And so, yeah, so we did it that way. And then we also ran experiments where we would modify all of the parameters, and then verify the amount or modify the amount of noise we added. If that answers the question, Philip, you may be able to hop on and explain that if I didn't characterize it well.
Perhaps we should say like we draw the random noise out of a normal Gaussian distribution. That's why if you modify like the mean and the standard deviation, then you get, of course, different sizes of the noise. But apart from it, it's exactly what you said.
Yeah. I guess like one more question from me is like, I would love to know like which part of the project actually turned out to be very, or like something that was more difficult than the others. I would think it's experimentation, but would love to hear your thoughts as well, since you sort of have to keep running keep running experiments over and over again, right?
So I'll start, and then Philip, you can. I'm sure you ran into difficulties too. I part of my project was applying this to the 5-3 small, and I want to emphasize like how stubborn it was. It would not follow my directions to perform poorly, and it was just very strange. I had to spend like an hour just like perfectly crafting a prompt to get it to Sandbag, and so that wasn't something that I expected at all. So that was like I knew the other parts would be fairly difficult. This was like something I thought would be easy. It ended up taking some time. And yeah, Philip, you can hop on.
Yeah, I mean, we had an interesting discussion in our group, and that's why we also chose like these two extremes of like modifying all weights and only a subpart of it, because like I had like more in my mind this mechanistic interpretability thing, that there are some circuits which might be responsible for sandbagging, and we want to hit these circuits with some noise. So you apply it to a small percentage of the model, you just run it often enough, and then you hope at some point you hit the circuit. And then more on the Nathan side, it was like more like, no, this is the wrong approach. We should modify all of them. And he had also a perfectly valid explanation. And we were like, okay, what to do? And then we said, okay, you are doing that, we are doing that. And surprisingly, we found the same result. A little bit different, of course, the noise levels and these things. And you also find the graphs in this thing. And we were like, okay, what's now the explanation? Like, where does it come from? And I think this is like, from the theoretical side, this is something which I find very intriguing.
Yeah, definitely. But yeah, congratulations to the team, and you should be really proud of yourselves for, pulling this off in 2 days.
Yeah. No, thank you guys. Yeah. Many thanks to the Apart team.
Yeah, and I'm going to shift you folks to the audience, and we will just cover some honorable mentions and, what we can, what you folks can possibly do with your projects and what you submitted to your hackathon as well. But yeah, thank you again. Awesome. Let me go ahead and share my screen. Feel free to add your questions, and maybe the teams can still answer it. So yeah, I know there were a lot of wonderful submissions over the weekend. So we do have some honorable mentions. First is The Werewolf in the House Always Wins for great game-based deception, evaluation, and detection. I think what was interesting is that they used like a game-based approach for measuring detection, and I think like they also sort of showed the fact that state-of-the-art models perform no better than random baselines and remain like incapable of collaborative deception. And yeah, it was something I think like really deserved attention. And so yeah, thank you so much for submitting that. And the second one is actually like truthful suffixes for a direct black box method to mitigate deception. This again was a great project because it sort of goes over sort of constructing truthful suffixes to make models provide more truthful responses. It's also like a black box method for reducing deception, and their work extends prior work on like adversarial suffixes for jailbreaking to sort of promote honest behavior. So yeah, wonderful work, the team behind this as well. The next one was detecting lies of omission for its great conceptual analysis of a problem. And I think something really nice about it was it sort of investigates deceptive omission, which denotes like a non-lying deceptive behavior. They also sort of modified and generated a data set that is targeted towards identifying deception that doesn't sort of involve outright lying. And then finally, we also have evaluating steering vectors for its expert evaluation of different steering methods for deception, mitigation, and detection. This team used like state-of-the-art steering methods to find and control deceptive behaviors in LLMs. They also released a new deception data set and demonstrated like the fact that the data set and the prompt formatting used actually when evaluating help to I guess like evaluate the efficacy of the steering methods. So yeah, thank you again team for like again like all of you had wonderful projects, and that's why we also took out the honorable mentions. And just to cover the last few slides on what are the next steps for the teams as well. You can like submit your ideas and results to AI safety idea list, share your work in the community server. That's like a good way to also like elevate your work and make sure it gets recognition in like online communities and global events. Read books from AI safety, publish your work perhaps on alignment forum. That's like a great place to also get feedback apart from online communities. And yeah, finally, you can go ahead and submit our feedback survey. I'll go and add it to the chat, and we will also send out an email to the winners with next steps. So yeah, stay tuned for the next hackathon. And again, thank you so much everyone for joining in.